Hello, my name is Hyung-Gyu Lim, working at GFDL. So it's my pleasure to join the SCOR Cice2clouds working group to introduce my topic about Arctic Ocean and sea ice and marine biogeochemistry works. So in summary, I will introduce three papers very briefly about the sea ice and phytoplankton coupling related to ocean mixing and nutrient supply. And second, is ice phytoplankton coupling in changing climate with anthropogenic carbon dioxide, CO2. And finally, we should further consider the atmospheric and riverine nitrogen influx into the Arctic Ocean in the changing climate. So first, Lim et al. 2019, the paper suggested that the cooling effects of sea ice phytoplankton coupling in the Arctic Ocean. So varying the chlorophyll can reduce the shortwave attenuation in the Arctic Ocean surface. So they have two possible mechanisms. The first is that the attenuation rate of shortwave penetration is changing depending on the chlorophyll changes, but exponentially. So this curve represents some idealized shortwave heating rate associated with the chlorophyll changes. So fixed chlorophyll and its shortwave attenuation rate is always on the curve. However, the average shortwave heating rate of this curve is always below than the curve. And another mechanism we found is that the high sea ice and ocean mixing to nutrient supply help phytoplankton growth rate. In contrast, the high sea ice can reflect the more shortwave based on the high albedo coefficient. So shortwave input into the Arctic Ocean layer will be less than the lower sea ice condition. So therefore, this negative covariance between the chlorophyll and shortwave flux anomalies for shortwave heating eddy term is always negative. So these two nonlinear effects of chlorophyll can reduce the heat capacity in the Arctic Ocean layer. Therefore, the marine ecosystem variability can play a role to sustain the cold Arctic climate to be sustainable. Okay, next is that we could further consider the anthropogenic carbon dioxide, CO2. So anthropogenic CO2 release the long wave radiation into the Arctic Ocean. So the atmospheric heating can melt more sea ice and increase the Arctic temperature in the atmosphere. So in spring season, the melting sea ice help to get more light availability for the marine ecosystem autotroph and photosynthesis. So it is more favorable condition to grow the phytoplankton in the springtime. However, in summer season, the melting sea ice can lead to the stabilized ocean in the Arctic regions. So nutrient supply can be decreased due to the stratification in the future climate. So as you can see, the nitrogen will be decreased a lot throughout the ocean layers. In addition to the mean state change of the chlorophyll concentration, we found the aforementioned the nonlinear rectification effects will be decreased, which means net heating effect from interaction between sea ice and phytoplankton in the future climate. So this effect can amplify further Arctic warming, especially 1.2 degrees Celsius in the Barents Sea and about 1 degree Celsius in the East Siberian Chukchi Seas. So finally, I would like to introduce some recent topic is that we found the current generation Earth system model do not consider the anthropogenic nitrogen flux changes through the atmospheric and river discharge. We further investigate the impact of the anthropogenic nitrogen depositions and riverine delivery into the Earth system model. So this forcing is generated by the Chemistry Climate Model Initiative, CCMI, developed by the Michaela Hagelin at Reading University, which is for the IPCC AR6 report, CMIP6 future projections. If you see very closely for this forcing, we can see that very strong signal for the atmospheric deposition to increase this high nitrogen flux near the Calabaran Sea, especially very close to the European regions. So we found that this anthropogenic nitrogen near the Calabaran Sea, even somewhat including near the East Siberian Sea, can be warmed faster due to the nitrogen flux increases. But the regional sensitivity are depending on the seasons because nitrogen was quite limited. That creates more chance to chlorophyll bloom. So this bloom can increase more shortwave, attenuation coefficient of shortwave penetration and increase of Arctic Ocean heat storage. So strong positive ice albedo feedback can amplify this anthropogenic nitrogen, chlorophyll, shortwave heating, and sea ice melting feedback processes in the future. So we should further consider these biogeochemical exchanges from land, river, and atmosphere into the Arctic Ocean. So in conclusion, we have to understand DCI's biochemistry and land-atmosphere coupling. The comprehensive Earth system modeling should be required to overcome the limitation collecting observation data set in the Arctic Ocean. And Earth system modeling can help the efficiency to collect the data set in the Arctic regions. What could be critical and urgency for the Arctic science communities? I'm currently collaborating the Earth system modeling in the Arctic Ocean and even Antarctic Ocean as well to understand the freshwater flux forcing, which is not included in the CMIP6 class Earth system model yet, to understand the Arctic system and better future projection based on the Earth system modeling efforts. So I will stop here and thank you for your attention.